Quantum computing. It's a term that gets thrown around a lot, often surrounded by a mysterious aura of immense power and mind-bending physics. But what exactly is it? Is it just a faster version of the computers we have today, or something fundamentally different? In this video, we're going to pull back the curtain on this exciting field, demystifying the core concepts and then diving deep into one of its most famous and powerful algorithms, Grover's algorithm. Get ready to understand the future of computation. To understand quantum computing, we first need to understand its fundamental building block, the qubit. Our everyday computers use classical bits, which can only be in one of two states at any given time, a 0 or a 1. Think of it like a light switch that's either on or off. A qubit, short for quantum bit, is different. Thanks to the bizarre rules of quantum mechanics, a qubit can exist in a superposition of both 0 and 1 simultaneously. This isn't just a fancy way of saying it's unknown, it genuinely exists in both states at once until measured. This is the first key to quantum power. Let's unpack superposition a bit more. Imagine a spinning coin. While it's in the air, spinning rapidly, you can't say it's definitively heads or tails, right? It's effectively both until it lands. A qubit in superposition is similar, but far more profound. It's not just uncertain, it literally embodies all its possible states at once. This means a single qubit can hold more information than a classical bit. 2 qubits can be in 4 superposed states simultaneously, 3 qubits in 8, and so on. This exponential growth in potential states is where the power begins. Beyond superposition, there's another quantum phenomenon crucial for quantum computing: entanglement. Imagine you have 2 perfectly linked dice. If you roll one and it lands on a 6, you instantly know the other one, no matter how far away, will also land on a 6. They are correlated in a way classical physics can't explain. Entangled qubits share this deep connection, they become intertwined, and the state of one instantly influences the state of the other, even when separated by vast distances. This spooky action at a distance, as Einstein called it, allows quantum computers to perform incredibly complex computations by correlating information across multiple qubits. So, with superposition and entanglement, quantum computers can explore many possibilities simultaneously and correlate information across them. This allows them to tackle certain types of problems that are intractable, or practically impossible, for even the most powerful classical supercomputers. These include complex simulations in drug discovery, materials science, optimizing logistics for global supply chains, breaking certain types of encryption, and much more. While still in its early stages, quantum computing promises to revolutionize fields we can only begin to imagine, opening doors to scientific breakthroughs and technological advancements. Now that we have a grasp of the basics, let's explore a specific example of quantum power in action: Grover's algorithm. Developed by Love Grover in 1996, this algorithm provides a quadratic speedup for a very specific, but incredibly common, problem: searching an unsorted database. Imagine you have a massive phone book where names aren't in alphabetical order, and you only know the phone number. A classical computer would have to flip through pages one by one. Grover's algorithm finds the name significantly faster by leveraging quantum principles. To appreciate Grover's algorithm, let's first consider how a classical computer would solve this unstructured search problem. If you have a list of n items and you're looking for one specific item without any order, the classical approach is called a linear search. You start at the beginning and check each item one by one. In the worst-case scenario, you might have to check all n items to find the one you're looking for. On average, you'd expect to find it after checking about n/2 items. So, if your list has 1 billion items, it would take roughly 500 million checks. That's a lot of work. Here's where Grover's algorithm shines. Instead of needing n/2 or even n operations, Grover's algorithm can find the item in approximately the square root of n operations. For a list of 1 billion items, that's roughly 31,622 operations instead of 500 million. That's a massive difference. How does it achieve this? It doesn't check every item in superposition. Instead, it subtly enhances the probability of measuring the correct answer in just a few clever steps. Think of it as not trying every key, but somehow making the right key glow brighter in the dark. The core of Grover's algorithm relies on a component called an oracle. This isn't a magical seer, it's a special quantum operation or subroutine that identifies the marked item, the one we're searching for, without actually revealing it. It does this by flipping the phase of the target state's amplitude. All other states remain unchanged. You can imagine the oracle as a black box that, when presented with the right input, gives a specific sign that distinguishes it from all other possibilities. This sign is crucial for the next step. Once the oracle marks the target state, Grover's algorithm uses a technique called amplitude amplification. This is the iterative process that boosts the probability of measuring the correct item. Each iteration consists of two main parts. First, the oracle marks the solution, then a diffusion operator effectively rotates the overall state of the qubits. This rotation shifts amplitude from the incorrect states to the correct one, making its probability of being measured much higher with each step. After a relatively small number of iterations, proportional to the square root of n, a measurement is highly likely to yield the correct answer. Let's summarize Grover's algorithm into these simplified steps. First, we start by placing all our qubits into a superposition of all possible states. Imagine every possibility is equally likely. Second, we apply the quantum oracle. This step marks the solution state by flipping its phase without disturbing the others. Third, we apply a diffusion operator, which performs the amplitude amplification, taking probability amplitude from the incorrect states and adding it to the marked, correct state. We then repeat the oracle and diffusion operator steps a specific number of times, approximately the square root of n. Finally, we measure the qubits, and with high probability, we will find our correct item. Grover's algorithm, while incredibly powerful for unstructured search, isn't a magic bullet for all problems. It's particularly useful for searching large, unsorted databases or solving optimization problems that can be framed as a search. Potential applications include breaking certain cryptographic systems, accelerating machine learning algorithms, or finding optimal solutions in complex scheduling. However, building stable quantum computers that can run Grovers for truly massive datasets is still a significant engineering challenge. We're on the cusp of an exciting new era, where quantum computers will complement, rather than replace, our classical ones, solving problems previously thought impossible.